Materials supplied by Microsoft Corporation may be used for internal review, analysis, or research only. Any editing, reproduction, publication, rebroadcast, public showing, internet, or public display is forbidden and may violate copyright law.
All right, so let's start. It's my pleasure to introduce Julian Moraro. Julian's a final year grad student at CMU, where he works with the recently tenured Professor David Anderson. Julian's interests are in distributed systems, and early on in his grad career, he also looked at designing, cute data structures for solving problems that were in the realm of machine learning, and applied them to a really scalable virus scanner that was developed at CMU. His PhD thesis focuses on improving this glorious protocol that we all know, Paxos, and Julian's going to talk to us about that today. So please help me in welcoming Julian.
Thank you. Thank you, Omar. Thank you for having me here. So this talk is going to be about revisiting Paxos. And I'm going to try to convince you that that's indeed as exciting as that sounds, just not in that way. So the general topic of my thesis work is fault tolerance in distributed systems. And like fault tolerance in most other fields, this is all about redundancy. The way we achieve redundancy in distributed systems is through state replication. That means replicating the state of a process onto multiple machines so that if some of these machines fail, the remaining ones will be able to continue handling client queries and commands just as the failed ones would have. And to keep the state of these processes in sync, we make them behave like state machines that change their internal state only as a result of executing the commands proposed by the clients of the system. And then if we make sure that they execute the same commands in the same order, then they will transition through the exact same sequence of states. And this approach is called state machine replication, or SMR for short. And state machine replication is important. For example, in local area clusters, state machine replication is used for operations as diverse as replicating data, resource discovery, distributed synchronization. And because we build larger and larger clusters, there is increasing pressure on these implementations of state machine replication to have both high throughput and high availability. And these are some of some real-world systems that implement state machine replication for these operations. We also use state machine replication in the wide area because we have clients on different continents accessing the same databases. So we want to bring that data closer to clients, and we also want to be able to tolerate full data center outages. And because in this setting, distances are so large, any inefficiency in unnecessary message delays or round-trip times to commit are going to have a high impact on latency. So it is critical in this setting for our implementations of state machine replication to have low latency. Spanner, Megastore are well-known systems that implement state machine replication for geo-replication. And implementing state machine replication, so there are multiple ways to do it, and they range from simple primary backup protocols to more complex protocols such as Paxos and Byzantine fault tolerance. Now, all the systems that I presented on the previous slides, they implement Paxos or protocols that are very similar to Paxos. And the reason is Paxos has a nice balance between safety, which is to say what kind of failures it can tolerate, and performance. And what I mean by performance is Paxos and Paxos-like protocols are fast. They are faster, or at least as fast as a simple primary backup, and they do not depend on external failure detectors, which make them have very high availability. And here's an example of what I mean by that. Let's say we have a primary backup system. If there's a network partition, and we let the clients continue to talk to both the primary and the backup, their states will diverge, which is exactly the opposite of what we want to achieve. So what do we do in this setting? We have an external entity, this external failure detector, which decides that, for example, the primary has officially failed, and the backup is the new authoritative copy of the data. And then the clients will learn from this external failure detector that they have to talk only to the backup. But of course, it takes a time between the network partition setting in, and the client switching to talking to the backup, and that's a window of time where the system is essentially unavailable. In Paxos, we don't have that problem because we use more resources. So here we have 3 replicas instead of 2 to tolerate a failure. But any of these replicas appearing to have failed, or any network partition setting in, will not cause the majority to stop working. And in fact, we don't have to declare failure synchronously. If a replica appears to have failed, we just continue going the majority. Because of this reason, Paxos has high availability, almost essentially constant availability, or in other words, instant failover. And this brings me to the overarching goal of my thesis work. So in my thesis work, I want to improve state machine replication, specifically Paxos-style state machine replication. And by that I mean systems that tolerate benign failures, so non-Byzantine failures. And by Paxos-style, I mean systems that use quorum consensus. I want to improve it on multiple practically important dimensions, but at the same time in a way that is well anchored in theory. And here's what I mean by that. So a Paxos system has essentially 2 components. There's this nice, elegant core, which is this general algorithm, the Paxos algorithm. And then there are a bunch of implementation considerations, right? How do we choose to implement a certain feature? How do we optimize a certain performance characteristic that's important in our system? And I want to improve state machine replication in a way that also expands this nice, elegant algorithmic core to include more of the practical implementation considerations, because I want the result to be easily applicable to a wide range of applications. So in this talk, I'll present the 2 main components of my work so far. They are Egalitarian Paxos, which is a new state machine replication protocol based on Paxos. It has lower latency, higher throughput, and higher performance stability than previous state machine replication protocols. And I will also talk about quorum releases that address an orthogonal performance characteristic of state machine replication. That is, how do we read really quickly from replicated state machines? So I'll start with Egalitarian Paxos. Before I get to Egalitarian Paxos, it's useful to go through a quick overview of Paxos. So Paxos is, at its core, an agreement protocol used by a set of distributed processes to agree on one thing. It tolerates F failures with a total of 2 F plus 1 replicas, and that's optimal because remember, we don't depend on external failure detectors. And replicas tolerate only, Paxos tolerates only benign failures, non-Byzantine failures. Machines can fail to reply for an indefinite amount of time, but they will not reply in ways that do not conform to the protocol. Also, communication is asynchronous. So for Paxos to be safe, we don't make any synchronicity assumptions about communication. However, for it to be live, there have to exist this window of times where there is synchronicity. So how do we use Paxos? This protocol that, as I said, at its core, it's a consensus protocol. It lets us agree on one thing. How do we use it to agree on a sequence of things? Right? That's what we want in state machine replication. And I'm going to show you this through an example. Let's say we have 3 replicas, and this is the replicated state. Everyone has a copy of this. Initially, all these command slots are empty. Right? They are ordered command slots. Clients talk to the replicas. They propose commands. And these replicas will contend for these preordered slots, and they will do so by running Paxos. As a result of running Paxos, only one of these replicas will win. That's that slot. Everyone will know which replica that is. Everyone will know what command went to do that slot. The replicas that lost that slot will contend for a different slot, and so on. They will do so by running Paxos. Now, when a contiguous sequence of slots has been filled, every replica can independently execute the same commands in the same order, thus ensuring that their states will remain in sync.
So are you implying executing both Paxos phases on every command, or are we not really doing that?
I'm going to get that to the next slide. So this is like the canonical execution of Paxos.
No, right.
So the takeaways here are that in Paxos, in canonical Paxos, we use a separate instantiation of Paxos to decide every slot, and that it takes 2 round trips to commit a command because the first round trip is necessary to take ownership of a slot, and then only after we've taken ownership, only after replica has taken ownership, can it propose the command. But of course, as you remarked, this is inefficient because it takes 2 round trips. So practical implementations of Paxos actually implement something that's usually referred to as multi-Paxos. And in multi-Paxos, one of these replicas is the pre-established owner of all the slots. So for example, in this case, the green replica is the pre-established owner of all the slots. And then clients talk to only this replica, this one replica, which will decide which commands go into which slot. And it will be able to do so after just one round trip because, again, the first round trip was to take ownership of a slot. That's not necessary here anymore. It is already the owner. But unfortunately, the single leader replica, as I'm going to refer to it in this talk, can be a bottleneck for performance and availability. Right? It has to handle more messages for each command than all the other non-leader replicas. And if it fails, there's a window of time when there's no leader, before another replica is elected as leader. So the question motivating this research is, can we have it all? Can we have this high throughput and low latency given to us by multi-Paxos? But at the same time, we want to preserve the constant availability of canonical Paxos. And we want to, furthermore, be able to distribute load evenly across all our replicas so that we use our resources efficiently and get high throughput. We also want to use the fastest replicas. Perhaps in our system, there are concurrent jobs running on some of these replicas, and we might want to avoid those replicas that experience high load when we commit commands.
So let me ask what you mean by constant availability in standard Paxos. In particular, it seems to me that, if I remember the way you described it, clients just send their commands to some replica.
That's right.
And then the replica tries to contend for the next slot, right? It runs phase one.
Correct.
If the client chooses a replica that's failed, then obviously that replica is not going to do anything.
That's right. So for that client, it might appear that the whole thing is unavailable.
Right.
But for other clients,
it retries and picks a different
right.
potential one. So I guess the question is that really better than using multi-Paxos?
Well, it matters in that other clients that have not been unlucky to choose that replica that has failed will choose replicas that have not failed, and for them, the system will be available.
Yeah, but doesn't it come out in the wash? Because what will happen then is in the canonical Paxos scheme, when you take a replica failure, until you have a timeout that causes the client to change it, let's say it's a size 3 group, a third of the clients will see unavailability.
Right. That's right.
Right. In multi-Paxos, if you take a replica failure, 2/3 of the time you're not going to lose the leader, and so it'll be no effect at all. And 1/3 of the time, everybody will slow down.
That's right.
So when you multiply those out, they come out the same. So
that's right. But I'm talking not about the sort of like what happens if you take the whole thing over a day, right? I'm talking what happens in that moment. And in that moment, 1/3 of the replicas for canonical Paxos will experience higher latency for those commands, whereas the other third of the replicas will not experience that. For multi-Paxos, when the leader fails, every client will experience higher latency for all their commands. And that's why I call.
This is true, but it only happens a third as much.
That's right.
Because it's only a third as many leaders as total replicas. So we wind up with. I mean, it's not clear that it's that much better, right?
That's what I mean.
It's not necessarily worse.
No, but I think we agree on what I define by unavailability. I mean that all the clients cannot do anything for a period of time.
All right. If you define availability as some client is able to do something,
that's right. Then
canonical Paxos is better than multi-Paxos.
That's right. Exactly.
Okay, cool. All right.
And you may argue that that's not enough, but that's what I mean here.
It's not clear that it's actually in practice any better, but
okay.
But I'll give it to you. I understand what you're saying.
Okay.
Good.
So the last property that we want is to be able to use the closest replicas, because in wide area replication, we want to commit commands after talking to our closest neighbors instead of having to go perhaps to a neighbor that's furthest away. So as I said, canonical Paxos has these properties, but because of the 2 round trips, it's not exactly efficient, right? It doesn't have high throughput and low latency. Multi-Paxos solves that, but it loses these other properties in the process. Now, by contrast, Egalitarian Paxos has all the properties that I've mentioned, and it implements them efficiently, so much so that it has higher performance than multi-Paxos. And EPaxos is all about ordering. So we've seen that previous strategies included contending for slots, as was canonical Paxos. One replica decides, and that's the case for multi-Paxos, but also for other versions of Paxos like fast Paxos and generalized Paxos. And finally, a newer version, a newer protocol based on Paxos called Mencius, has this property that replicas take turns in committing commands. So it is pre-established that the first replica is the leader of every third slot starting at 1. The second replica is the command leader for every third slot starting at 2, and so on. And Mencius is effective in balancing load because at the same time, there will be many commands being proposed concurrently, and all the replicas will be leaders for some commands and acceptors for other commands. Unfortunately, in Mencius, the whole system runs at the speed of the slowest replica because we cannot decide a slot, we cannot commit it until we've learned what happened in all the previous slots. And the previous slots belong to all the replicas, so a third of the previous slots belong to every replica. Furthermore, any replica being unavailable causes the whole system to be unavailable because of the same reason.
Which makes you wonder what the point is.
Better throughput. It does have better throughput.
Okay, as opposed to just doing single machine. Anyway, okay, right. That's not your...
It is effective in
right.
balancing load. So in EPaxos, we take a different approach. Instead of having a linear sequence of pre-ordered slots, we split that space into as many subspaces as there are replicas. And we give pre-established ownership to each replica over one of these rows. So this is the replicated state. Everyone has a copy of all of this bidimensional array. And clients will propose commands to any replica of their choosing, and that replica will get that command committed in one of its own slots, so a slot that belongs to its own row. For the green replica, that's the first row. And so on, and this is good because there's no longer contention for slots, but it's no longer clear how do we order these commands, right? Like 3.1 comes before or after 2.2. So the way we do it is in the process of deciding what command is to be committed in a slot, we also decide ordering constraints for that command. This means that B has an ordering constraint on A, so B should come after A, should be executed after A. And we do this for every command. And when these commands have been committed, every replica sees the same command in the same slot and with the same ordering constraints. So they can independently analyze these constraints and come up with the same ordering. So the takeaways here is that we achieve load balancing because every replica is a command leader for some commands. And we have the flexibility to choose any quorum of replicas, any replicas to be part of a quorum to commit a command. We no longer have to involve one particular replica on every decision, like it was the case for the stable leader in multi-Paxos. Question?
Is there an assumption that a client is only sending one command at a time to the cluster? I mean, if I'm a client and I have a set of commands that are dependent upon one another, and I send them to different replicas that aren't communicating, I could have those operations commit out of order in terms of the client's expected serialization.
So I'm not sure I understand the question. Was your question, are clients sending commands one at a time? And the answer is yes.
So they wait. They wait until the prior,
right.
So you can't pipeline commands.
If it is important for them that some commands are executed in a particular order, then what they do is they have to wait for the first command to be acknowledged by the system before they propose the next command.
Is that rule for all versions? Because multi-Paxos, it seems like that wouldn't exist because I can, since I'm serializing through a leader, I can sequence them and I can be sure that one will be executed.
You can't really.
Really?
Right. So like in Smarter, it doesn't work that way.
Right. So even in multi-Paxos, you don't get that guarantee.
And the reason is you might change leaders if one command and the other.
That's right.
So Smarter lets clients pipeline, but the ordering guarantee that you get is that anything that you send down is ordered after things that you've already seen completions for. Okay. So you can send out as many as you want, but they'll execute in whatever. It's just like doing disk I/O asynchronous system calls. Right?
Well, unless you have an unless you have
something
unless you express
it's not like that.
I understand.
Okay, so I was saying that.
And can you do that, by the way? Can you do the same thing where a client can pipeline if he doesn't care about the order of the commands?
Sure.
And they still wind up serialized.
They wind up serialized, but not
not
necessarily linearized. So there's no,
Right, that's
yeah.
right.
Yeah.
So in Paxos, you have to couple serialization guarantees with commit guarantees, similar to ordering and durability. They're unnecessary. You could argue they're unnecessarily coupled. Okay.
So as I was saying, we have the flexibility in EPaxos to choose any replicas to be part of our quorums. No longer is there a special replica that has to be part of every decision, right? Like a stable leader, and we don't have to get some information from every other replica in the system, like was the case for Mencius. And this has important implications for performance stability, because we'll be able to avoid replicas that are slow or unresponsive, and for wide area latency, because we'll be able to just talk to our closest neighbors. Question, yes?
Where these orderings come from, right?
Excuse me?
Well, the important question here is how are the dependencies determined?
Right, I'll get to that in the next
Okay,
slide.
okay.
What's your question?
All right. And maybe this is something you could answer at the end of the talk, because it's a. You're saying you want to combine low latency and high throughput. I'm just wondering if maybe at the end you could take a few minutes to talk about what scenarios where a high throughput Paxos system is important.
I think the simple answer is, in a local cluster, probably throughput is more important than latency, whereas in the wide area latency becomes very important. Just because any sort of like mistake or inefficiency that we make is going to cost us a lot, tens of milliseconds.
When we did Smarter, we had it back at disk. High throughput was really important because SQL Server kind of big cared.
Okay, so to go into more detail of how do we set these ordering dependencies, I'll go through an example. This is a time sequence diagram, time flows from left to right. We have 5 replicas, and let's assume that there's a command A proposed at replica 1. Replica 1 at this point has seen no other command, so it says pre-accept A. That's how we call these first round messages. We call them pre-accepts. So take A with the dependency that it depends on nothing. So essentially there's no ordering dependency at this point. It sends this pre-accept to a majority of replicas, that is itself and to other replicas. The replicas R2 and R3, they agree because they haven't seen other commands. Because these two acceptors agreed with each other, R1 can commit locally and notify everyone else asynchronously. Now let's assume that at about the same time there's another command proposed at replica 5 saying, command B. R5 has not seen anything for A, so it says B depends on nothing. R4 agrees, but of course R3 has seen a pre-accept for A, so it says B has to depend on A. Because the two acceptors, R3 and R4, disagreed with each other, R5 has to take the union of these constraints and use a second round of communication saying that these are the final ordering constraints. And the replicas that receive these accept messages only have to acknowledge accept messages. So they don't have to update these ordering constraints anymore, even if there are some other commands being proposed concurrently. So they only have to acknowledge. When they have acknowledged, R5 can commit locally and notify everyone else asynchronously. And one last example, let's say C is proposed at replica 1. R1 has not seen any message for B, so it says C depends only on A. And then R2 and R3 have both seen commits for B before getting the pre-accept for C, so they say C has to depend on both A and B. Because the two acceptors agreed with each other, R1 can commit locally and notify every other replica asynchronously, including the client. So a simple analysis of this protocol shows you that when commands are non-concurrent, it'll take one round trip to commit. But when commands are concurrent, some of them might have to undergo 2 rounds of communication until commit. And that seems like a bad thing, right? That's what we wanted to avoid with canonical Paxos, essentially.
Just to be clear, this does result in a total order, right? You never wind up with for any pair of reads, I can always, operations, I can always tell you what order they're in. They're always ordered relative.
That's right.
Yeah.
That's right. Now, to our rescue comes this observation made by generalized Paxos before us and by generic broadcast protocols before generalized Paxos, which is that we don't actually have to order every command with respect to every other command. We just have to order those commands that interfere with each other. And an intuitive way to think about this is that we only have to order those commands that refer to the same state. If they don't refer to the same state, for example, if we have two puts in a replicated key value store to different keys, it doesn't matter in which way we execute them on different replicas. As long as we execute them both, we will get the same state. So then what this means for our system is that we'll be able to commit commands after just one round trip if they are either non-concurrent or concurrent but non-interfering. And we'll take 2 round trips only for those commands that are both concurrent and interfering. And it turns out that in practice, it is rarely the case that concurrent commands interfere with each other. The next logical question is, how do we determine whether commands interfere with each other before executing them? Because remember, we first have to order these commands, and in the ordering process, we have to determine whether they interfere or not, and only then can we execute them. Now, the answer is application specific. For NoSQL systems that are variations of key value stores, it is very simple because we just look at the operation key. If 2 operations have the same key, then they will interfere. Otherwise, they don't. Another approach that we can take is the one taken by Google App Engine, which requires developers to specifically specify which sets of transactions interfere with each other. And finally, it is possible to infer interference automatically, even for more complex databases, like, for example, relational databases, because it turns out that most OLTP workloads have these simple transactions that are executed most frequently, and they are so simple that we can analyze them before executing them and tell with certainty which tables and which rows in which tables they will touch. So for these simple transactions, we'll be able to determine whether they interfere or not. And for the remaining transactions, which are more complex and perhaps we cannot analyze beforehand, we can safely say that they interfere with everything else. OK, so we've gotten these dependencies. How do we actually order the commands? And this, again, is an example with 5 commands, A, B, C, D, E. And the edges here are meant to signify dependency. So A has a dependency on B, B also has a dependency on A, and so on. So the first thing we do is we find the strongly connected components. And then because this graph where SCC's strongly connected components are these super nodes, this graph is a DAG, it's a directed acyclic graph, we can sort it topologically and execute every strongly connected component in inverse topological order. When there are multiple commands in a strongly connected component, we use another ordering constraint that I haven't described. We call it an approximate sequence number. But a simple way to think about it is just a Lamport clock. And that's what it is essentially. And we execute an increasing order of this approximate sequence number. So what we get is...
Can I ask you a question? You just moved a little too fast for me. So what's a dependency? Is that an interference? Because you started using the word dependencies in the previous graph.
Mm-hmm. No, so dependency is an ordering dependency.
It's an ordering dependency.
It means that a command has a dependency on another command if, when committing this command, the second one, we saw something about the first command, right? So we added a dependency. Now, we only add dependencies if those 2 commands interfere, right? So commands interfere whether they refer, if they refer to the same state. If they interfere, then we add some ordering dependencies between them.
More particularly if they have either read-write or write-write interference.
Correct.
Right?
If they are both reads, it's not necessary. That's right. So the property is that, yes?
So wouldn't it be the case that analyzing interference takes longer time than round trip time?
For some applications, it may take longer time, right? My argument is that for many applications, it is actually very easy. Because we have things like operation keys.
So key value store, that's easy.
And even for relational databases. If you take the TPCC benchmark, which is very popular in the database community, it has one transaction, I believe it's called a new order transaction, which is very easy to analyze. And we can tell with certainty whether 2 of these new order transactions can interfere or not.
Right. Well, it depends at that point what you're considering to be the same thing, right? Do you mean the semantics are the same or the state stays the same?
I want to say that they commute.
They commute.
So that's the simplest way.
So this system will result in replicated state machines with a different state after the same set of operations because it executed in different order.
But that's the case for multi-Paxos too, just because not every replica has to execute all the commands at exactly the same time. As long as they will execute all the commands that have been committed so far, then they will have the same state.
If they execute all the commands in the same order, they'll have the same state, right? You can imagine, say, a page allocator that just grabs the next page and so you want to put things in different places.
Yeah.
And that only matters when you're trying to rebuild the state when you lose it.
I'm sorry, you're suggesting that...
So one of the things that we addressed in Smarter is that if you get into a situation where, say, a replica goes down for a while, right? I mean, it's not permanently lost, but it's off for...
Right, and it doesn't get some commands.
So you have two options, right? One is you can just save all the commands.
Oh, I see. Or you're saying you checkpoint the state and you send the state in bulk to the other.
Or you checkpoint the state and send the state in bulk.
You can still do checkpoints here.
So you can send the entirety of the state.
Right.
That'll always work,
Yeah.
even regardless of this. Or you can send only the pieces of the state
Sure.
that have changed. You can't do that here.
Absolutely,
So
but you can
lose the
checkpoint here. You can checkpoint. You can use the special checkpoint command that interferes with everything.
Right, but
And
the point is your states,
after you've executed that, you say,
your states will be different. So you
in between checkpoints, sure.
In between checkpoints. So it means that to bring back a replica, you either have to continue remembering all the commands, which results in unbounded storage, or you have to move all of the state.
No, you can move. You can remember all the commands from the previous checkpoint.
Well, that's what I meant. But,
Yeah.
but it obviously stops checkpointing when it stops running. So, I mean, it's not a terrible thing. But
Sure. Yeah. Since since the last checkpoint that it has observed. That's right.
Right. You just lose it.
That's right.
Something that's actually kind of handy sometimes. All right.
Okay. Yeah, that's right.
I'm just understanding.
Yes.
Can I ask one more question about the previous slide before I move on? I'm not sure I totally understand the semantics of a circular dependency there. We're trying to determine an order of the transactions.
So you're saying that, am I getting this correctly? You're saying that you don't understand why two commands might have a circular dependency, or are you saying what does that imply to ordering?
I guess both. It just says
So two commands may have a circular dependency if they, for example, if they are concurrent. But it can happen even if they're not concurrent, and they are concurrent with a third one, for example. But let's take the simple example, right? Two commands are concurrent. One of them sees the other on some replicas. The other one sees the second one first on some other replicas, right? Just because they don't receive messages for the same command. Replicas don't receive messages for the same command in the same order. Okay.
But I thought that was just a transient state. In other words, if there's disagreement, I thought you have to keep iterating until finally everybody agrees on it.
No, that's not what we do. We don't continue iterating. So we only at most execute 2 rounds. And then if after the first round, there's been disagreement, we take the union of those dependencies. And when we take the union, that's when we get the circular dependencies.
So, why don't you describe to me what these arcs are? Because I thought I understood them much, right? I didn't think carefully enough.
So,
what is an arc in this practice?
So this means that B got after E on some replica. Yeah, so some replica received some message for B after it has received some message for E.
Depends on E. So B depends on E?
So B depends on E, yeah.
So you're saying in this case circular is some replicas saw A before B and others saw the opposite?
Exactly.
Okay.
Yeah, I think the confusion was earlier Bill said at the end he said so this always establishes a total order and you said yes. And
it does establish total ordering because after you've executed this algorithm.
If you've executed this algorithm, but earlier before you described this algorithm.
Right. The first thing you showed does establish it. The two-round algorithm establishes a total order.
Only after we've executed this algorithm on the dependencies that commit protocol establishes.
So after the last algorithm you showed the other slides, you can still end up with a circular dependency.
Exactly.
So will every replica have the same graph?
Every replica will see exactly the same graph.
Right, but this graph allows you to be concurrent and executing it.
No, in this graph we assume that you can assume that they sort of all interfere with each other. So in the simplest way to imagine this, you have some commands that refer to object A, some commands that refer to object B. And they will have different disjoint graphs. Right? Of course, you can have commands that refer to both A and B. And that's when the graphs will be connected.
How is it possible that every replica will see the same graph? Because it could be that some of these replicas are not seeing some necessarily object.
Right. So those commands will be in different connected components and will have no bearing on
But
this.
they'll eventually come to the same order.
Right. Exactly.
Okay, I think I get it now.
Okay. So the properties that this whole commit protocol and execution protocol guarantee are linearizability, which is a strong consistency property. Linearizability implies serializability, and furthermore, it implies that if two commands interfere and one of them is committed before the other one is even proposed, A will be executed before B everywhere. And the second property, which is an important property, is the fact that fast path quorums for replicated state machine that tolerates F, concurrent failures. So fast path quorums will have to contain F plus ceil of F over 2 replicas, including the command leader. What I mean by fast path quorums, I mean how many replicas, including the command leader, have to agree on a certain set of dependencies for that command to be committed in the fast path. And that's the number of replicas. What this means is that for the most common deployments of Paxos, of 3 and 5 replicas respectively, this comes down to the smallest majority. So this is optimal. And it also means that it is better than fast and generalized Paxos by exactly 1 replica. In practical terms, this means that if we do geo-replication, and we have, let's say, a replica in Japan, 2 on the West Coast, So if we do geo-replication and we have a replica in Japan, 2 on the West Coast, 1 on the East Coast, and 1 in Europe, a replica in Japan will be able to commit a command after just talking to its closest neighbors, US West. It doesn't have to go all the way to Europe or all the way to the East Coast. So we've implemented EPaxos. We've also implemented multi-Paxos, Mencius, and generalized Paxos, and we compare them for a replicated key value store. So first I'm going to show you wide area commit latency. This is the setup that I've shown before. We have a replica in an Amazon EC2 data center in North Virginia, one in California, Oregon, Ireland, and in Tokyo. And this gives you a sense of the round trip times between those locations. Now, in this diagram, I'm going to show you the median commit latency as observed at every location for every protocol. We have clients co-located with every replica in each data center. And these clients submit commands, and then they measure the time it takes to get the reply back. So for a client in California, it has to wait for its local replica to talk to Oregon and Virginia. And that's also the case for a client of multi-Paxos, but only because the multi-Paxos leader is located in California. For a client that's in Virginia, that client has to first go to the leader in California, wait for it to commit the command, and then get back to Virginia. So it experiences higher latency. Mencius has higher latency because, remember, before committing a command, we have to wait for some information from every other replica in the system, including the ones that are furthest away. And generalized Paxos has higher latency than EPaxos because its fast path quorums are more numerous, are larger. And in fact, at every location, EPaxos has the smallest latency of all the protocols because it has optimal commit latency in the wide area for 3 and 5 replicas. Now, of course, this is median latency. When there's interference, when there's command interference, 99 percentile latency is going to be double this. However, there are ways to mitigate that, ways that we just haven't implemented yet. And we believe that command interference will be rare enough that it will affect at most the 99 percentile latency. Now, in the local cluster, we compare multi-Paxos, Mencius, and EPaxos to see how they fare with respect to throughput. This is a 5 replica scenario. EPaxos has different rates of command interference. 0% means that no commands interfere. 100% means that all commands interfere. And what you can see here is that EPaxos has higher throughput than the other protocols when command interference is low. Furthermore, when replicas are slow, and for the multi-Paxos here, the leader has to be slow for this to happen, otherwise the throughput remains the same. So when replicas are slow, and that replica is the multi-Paxos leader in multi-Paxos, the performance of EPaxos degrades more gracefully than for the other protocols. And the reason is we can simply avoid those replicas that are slower, whereas in the other protocols we cannot.
So
Yes?
question on the performance figures. So look at the top one. So
Yeah.
comparing multi-Paxos versus 100% EPaxos construction, right?
Yeah.
So the difference is like 10, 20%?
The difference here is, no, it's probably smaller than 10%.
Yeah, so can you comment on that?
So what happens here? So the reason why multi-Paxos is slow here is because all the decisions go through the leader, and the leader is CPU bottlenecked. The reason why EPaxos is slow here is because it has to do 2 round trips of communication for committing every command.
It uses all the 5 servers.
But it uses all the 5 servers.
So why is the difference so small?
You're saying it should be larger?
Yeah, right. Shouldn't.
I don't have the intuition of why it should be larger. So EPaxos does more work, but it distributes that work across all the replicas. Multi-Paxos does less work, but it concentrates that work to the leader.
So my practical experience with doing this is that the work of being leader is not very substantial.
So the assumption here is that the amount of work that you do on the leader is essentially it essentially has to do with communication, because executing the command, for example, or sending it to the disk, that's not the bottleneck in the system. If that is the bottleneck in the system, then these results would look differently.
What's the bottleneck?
Here is the CPU. The fact that you have to handle more interrupts on the leader.
So you're setting a number of operations per second that you're pegging the CPU?
No, so the operations are small enough that this workload is dominated by messaging.
So these are all writes, right? Not reads.
That's right.
Okay, and then if we look at the 0 confliction, and then it's only twice difference?
Okay. Almost twice, yeah.
Not 5 times?
No, it's not 5 times, because there's still some work that has to be done on every machine, and that work sort of like, so the amount of work that you do in total is more than the amount of work that you do in total in multi-Paxos.
So are you logging these, or this is?
In this case, they weren't logged. In our paper, we have comparison between them when we do log them synchronously to SSDs. And then the results are marked closer to each other. That's true, right? Because their logging is the dominant factor.
Right. I guess it depends on your application. You may not care about persistence.
That's the reason why I show you this graph is because I want to compare the protocols themselves, not necessarily the underlying needs of the applications, which may differ.
Sure. You said the dominant overhead in messaging is the time the CPU takes to service the message.
No. It's the fact that it has to handle more interrupts to reply to more messages.
Because there are more total messages in the protocol?
Because there are more total messages on one replica.
It's because the
Squarely
leader
on one
has to
replica.
receive the acts coming back from the others.
So a leader,
Assuming that's going to slow it down.
Well, it gets twice as many messages, or actually, no, it gets more than 4.
It does, yeah.
so the leader handles order n messages for each command, whereas non-leader replica handles order 1 messages for each command. That's where the imbalance comes from.
Actually, so the questions are not answered. Maybe you can revisit this particular pipeline. But I had one really quick question. So is in EPaxos, are the replicas actually measuring as they send out these messages to other replicas what the latency is?
No, here they don't.
So how do you determine the slow replica?
Oh, we send pings, and we measure how long it takes to reply to pings, echo messages essentially.
Is this done once? Or
It's done periodically, something like every 200 milliseconds or half a second.
And for the second experiment, you slowed down one of the replicas, is it?
Yes.
How did you slow it down? By reducing the throughput? Or
No, by having a CPU-intensive program, essentially an infinite loop running on the same machine.
And what was the networking protocol used to communicate here between?
What is the metric?
The network. What is the protocol?
Oh, it's an Amazon EC2 data center. I think it's. Yeah, I think it's 1 gig Ethernet, but that doesn't matter because the bandwidth was not the bottleneck.
No, but there is a TCP between these replicas.
It's TCP. Yeah. Okay, so now the intuition of so batching is an approach that we commonly use to increase throughput, and you might have the intuition that multi-Paxos might do better with batching because it has more of a chance to do to use larger batches, right? So the multi-Paxos leader receives all the commands. It can just commit all these commands in one batch in one round of Paxos, whereas in EPaxos we get the same number of commands distributed across multiple replicas, so there are going to be more batches for the same number of commands. This is a latency versus throughput graph. The y scale is the y-axis is log scale. This is the curve for multi-Paxos. Obviously, it's better to be lower and to the right because that means higher throughput, lower latency. EPaxos is significantly better than multi-Paxos. The reason is the communication with the clients is now shared by all the replicas instead of having to fall squarely on the leader. And perhaps counterintuitively, EPaxos 100% is almost as good as EPaxos 0%. The reason is communication, the second round of communication necessary to commit commands when there is interference, when there are conflicts, is spread across the large number. So the cost of that is spread across the large number of commands in a batch. Right? Second round messages are small. They don't have to contain the commands themselves anymore, just the revised ordering constraints. And finally, a nice side benefit, and this comes back to a discussion about availability, is that in EPaxos we have constant availability. And this will probably clarify what I mean by that. So let's say that we have, this is multi-Paxos, and what I'm showing here is throughput over time when there's a leader failure. A replica failure, a non-leader replica failure would not be seen here. So when there's a leader failure, the throughput for the whole replicated state machine goes down until the new leader has been elected. These are commands from the clients that have not been able to commit them in the meantime. In Mencius, any replica failing will have this behavior, whereas in Paxos, a replica failing will cause the throughput to go down by a third. In this case, we had 3 replicas. So the throughput goes down by a third because those clients that were talking to the replica that has failed have to time out and then talk to some other replica.
How well again, it's worth observing that in the multi-Paxos case, 2/3 of the time nothing happens.
That's right. So yeah, but when something happens, that's right.
It always does. So that
correct. But when something happens, that's more grave than when something happens in EPaxos.
But it happens less often.
That's right. So instead of conclusions for this part of the talk, I'm going to try to disentangle some of the most important insights into EPaxos. So the first one was we deal with ordering explicitly, instead of dealing with ordering implicitly by using Paxos on some pre-ordered slots for commands. And this gives us high throughput because we load balance better. It gives us performance stability because we have the flexibility to avoid slow replicas. And low latency because we can choose the replicas that are closest to us. Furthermore, it lets us optimize only those delays that matter. Previous Paxos variants that optimize for low latency, they try to do away with the first message delay between the client and the first replica. These are fast Paxos and generalized Paxos. Now, when we're doing wide area replication, where latency is really very important, that first message delay is going to be insignificant because usually the client will be co-located with its closest replica in the same data center. So instead of focusing on doing away with that message delay, we focus on having smaller quorums, which in turn gives us lower latency because we can talk to fewer of our closest neighbors. And we have a TR with a formal proof of correctness for EPaxos. It also contains a TLA plus specification that can be model checked. And we've released our implementation of EPaxos and all the other protocols open source. Yes?
Why is it called egalitarian?
Because replicas perform the same functions at the same time, sort of.
No leader.
Instead of having a leader that dictates. Okay, so to go back to the goal of my thesis work, was to improve SMR. And I think that Egalitarian Paxos goes a long way to doing so because it has higher throughput than previous state machine replication protocols. It has optimally low wide area latency for 3 and 5 replicas. And it offers better performance robustness, constant availability. And furthermore, there's no need for leader election. There's no leader. Now, can we improve other aspects of state machine replication? And a very important one that doesn't fall into this category is what happens when we read from the replicated state machine. So how do we improve read performance? Now, why is that different from command throughput, right? Because let's say that, so let's look at the different ways in which you can do reads from a replicated state machine. A simple way is to treat reads just like any other command. So if we have a client, that client may try to read from a replica. This, by the way, is multi-Paxos. So the discussion that I'm going to describe now for the second part of my talk applies to any Paxos type protocol. So in this particular case, example, this is multi-Paxos. So let's say that a client tries to read from a replica. That replica will forward the read to the leader. The leader will just commit it, just like it would do with any other command, and then would get back to the client with the result. Now, obviously, this involves a lot of communication. This is not ideal for wide area. A second, better way is to have the replica that got the read just talk to any quorum of replicas, for instance, its closest neighbors, and ask them, what is the latest command that you've seen? Wait for that command to be executed, get back with the result, and the replica closest to the client would perhaps reply to the client. This is less communication, fewer runs of communication, fewer message delays. It's better, but there's still some communication. So practical systems use leases. The most common variant of leases is leader leases, where the leader has a lease on all the objects in the system. As long as that lease is active, the leader can read from its local cache, from its local store. Now, even if the leader appears to have failed, the new leader will not be able to commit updates until the lease of the older leader has expired. In this case, the client can either read directly from the leader or have its closest replica forward that command to the leader and get it back. Obviously, the clients that are co-located with the leader will see very low latency. Other clients will see high latency. And the other previous way in which we had leases was described in Megastore. And these were leases where every replica in the system had a lease on every object in the system. This means that a client can just read locally from its closest replica, and that's great for reads. However, we pay the price when we do writes, because now every write has to go synchronously to every other replica in the system. We cannot commit that write until every replica in the system has acknowledged that write. So writes will have higher latency, and furthermore, when a replica is unavailable, the whole system is unavailable for writes. So if we look at the until the lease expires, exactly. So if we look at the design space for leases, so far we have these 2 points. We have the leader lease, which has almost the same write performance as a system that has no leases, and has better read performance than a system without leases, but the read performance is not great, right? We can only read locally from the leader. And we have the Megastore lease, where the read performance is great. We can read locally from every replica, but we pay that in write performance and availability. And in our work, we set out to explore the space in between. And I'm going to argue that we can do so with something that we call Quorum leases. And Quorum leases allow us to get the right trade-off for our application between read performance and write performance. And furthermore, I'm going to argue that they actually get us most of the performance, most of the benefits of both the Megastore and the leader lease. And the idea here is pretty simple. Instead of having one leader, one replica hold the lease, or all replicas hold the lease, we can let an arbitrary subset of the replicas hold the lease. Now, in particular, we make the observation that the fact that in Paxos we have to communicate synchronously with a quorum before we can commit an update induces a natural leasing strategy, and that is we simply take the smallest majorities, the simplest quorums, and we give them leases for objects. And in fact, we can have different quorums hold different leases for disjoint subsets of objects. And the assumption here is that different objects are popular or are hot at different replicas. imagine if we have, let's say, a replicated social network. It is more likely that the clients in Europe will have a different set of requests to the data center in Europe than the clients in the US would have for the data centers in the US. Right? So the assumption is that there's some geographic locality in our workload.
And that via reads that touch multiple objects. Like imagine that you have a B tree.
Absolutely.
Right? Everybody's going to touch the root.
Right.
So
when this happens too often, then we may not want to use that. When this happens infrequently, we can do two things. We can either pay the price with the write and just forward it to all the quorums that are pertinent to that composite update, or we can make sure that we configure the quorum such that objects that are usually accessed together are part of the same quorum lease.
Then the follow-up would also be based on what you're doing. Maybe you can pick the right strategy. If it's a read-heavy object,
right,
move this way. If it's a write-heavy object, move that way. If you're learning what is the
sure, like have a smaller quorum.
Like
exactly.
The tool will not be
right. So I guess what you're saying is that if we have a read heavy object, then maybe we'll give a lease for that object to more replicas. If it's a write heavy object, we'll give that read lease for fewer objects, for fewer replicas. That's true, right? That's a possibility.
So does this also mean that once you start doing this with read leases, before you're able to commit a write operation, you need to know the set of objects that it touches, because you need to know.
That's right.
Okay.
Yeah.
Which isn't necessarily an obvious thing in general state machine replication.
Not in general, but I think in many cases it's fairly easy.
Certainly, if it's a key value store, it's pretty straightforward.
That's right.
Okay.
Okay. So instead of describing in detail our design, I'm just going to lay out the challenges of implementing quorum read leases. So the obvious question is which quorums should hold the lease to each object, and it becomes quickly apparent that quorum leases should be dynamic. Before quorum leases, we had single leader lease, and every replica has a lease. All replicas have the lease, which means that it's very easy to decide who holds the lease, right? It's either the leader or everyone. But now we have to adapt to access patterns. We have to give the lease to those objects that need it more, right? To those replicas that read those particular objects more. So now the challenges become how do we establish, maintain, and update these leases, right? And by update I mean about establishing the timing information necessary to be able to expire the leases in a timely way, and also migrating different objects between different quorums. So we want to do this cheaply for millions or many millions of objects concurrently with minimal bandwidth overhead. So that's one challenge. And the other challenge, of course, is we want to do this while at the same time maintaining the safety of the Paxos protocol underneath the quorum leases and the safety of our leases, right? So we want every read to be a strongly consistent read. And I'm going to quickly show you some preliminary results that we've had. We've used the YCSB benchmark for a skewed workload. This is the ZPN distributed workload in YCSB. Again, this is the same setup for wide area. And we observed that every replica, not just one replica as the single leader lease, can do 60 to 90% of the reads locally. And furthermore, 60 to 90% of all writes have the minimum latency that we can get in a multi-Paxos system on this configuration. Now, we believe that with a bit more engineering, we can get this number to over 90% for the skewed workload for reads. And I think that should be pretty easy to do. In the local area, quorum leases also have the benefit of increasing throughput, read throughput. Because we can now do local reads at every replica, every one of our 5 replicas, read throughput increases by 4.6x.
Okay. That depends, right? Again, if you look at what we did with Reads and Smarter, we read from all of them. You use the leader to guarantee serialization, but you read from all the replicas.
But we don't do any communication for reads.
Right, but in the local area case, the communication is relatively cheap.
Not for throughput.
For throughput.
Now,
but you don't have to move
I understand your point, which I think it is, that we should compare against the reading strategy in Smarter.
Right.
And that's a valid point. That's right. We should do that, yeah.
Right,
yeah.
Which doesn't work very well in the wide area, but it wasn't designed to.
Right. No, I understand. Now, this number is about 20% lower than Megastore leases, right? Because Megastore leases have the best read performance, but we also don't have the problems for writes with Megastore leases, in particular the write availability problem for Megastore leases. So, in summary, I presented my work so far on improving state machine replication. I've shown you that we can get optimally low latency in the wide area, higher throughput, and higher performance stability with egalitarian Paxos. That we can get high read performance without sacrificing writes with Quorum releases. And I believe there's extensive room for future work here. I want to, in particular, study fast reconfiguration algorithms that have minimal impact on availability. I also want to study more uses of wall clock time beyond leases. What I mean by that is, let's say we had synchronized clocks. What can we do better? We know for sure that there are ways to implement EPaxos with synchronized clocks that are easier than just like a normal implementation of egalitarian Paxos. But conversely, if we don't have synchronized clocks and we want to get things like spanners, snapshot reads, can we do that with just Quorum leases? And I think there might be a way to do that. And finally, I'd like to be able to put this all together and provide general transactions on top of multiple EPaxos groups that also use Quorum leases. And the last slide I'm going to show you is to point out that I've also worked on other things, including hardware-aware data structures. In particular, this feed-forward Bloom filter. That's a variant of Bloom filters that has great benefits for multiple pattern matching, like, for example, malware scanning. And also on redesigning new systems around these new memory technologies, like phase change memory, memory stir. And if your interests are aligned with this, please ask me about it. Thank you.
Any more questions, clarifications? People want to go back to slides that Julian might have said. I'll ask later.
Yes.
So maybe it was something I didn't understand when you went through it was your use of vector clocks. In case you have a cycle in the dependency graph?
Right, those are not vector clocks. That's just a Lamport clock.
Okay.
Yeah.
So is that something that only works in this particular case, or is that something where you could use Lamport clocks to do ordering?
So let me see if I understand your question. You're saying, what if we use just the Lamport clocks and not use the other dependency thing with the graph and all the edges, right?
Yeah.
Yeah. So that's not possible. We've thought of that, but that's not possible. The reason why it's not possible is because the Lamport clock or that approximate sequence number for a particular command doesn't have to cover the entire space for that Lamport clock. So for example, if a command gets sequence 5, it doesn't necessarily mean that there have to be commands for 1, 2, 3, and 4. So we may wait indefinitely for something to be committed for 1, 2, 3, and 4. Yes?
So I don't have a question. I just have a question, a clarification question for me, and my question is actually to Bill. So if I understand this correctly, basically, this trades off the impact of failures by reducing that impact, but spreading it, making it more likely over time. Right. So why would it be better to actually increase the impact of failure, but reduces their likelihood? Like I'm struggling with. It seems like this trade-off is a better trade-off to me. Although I don't.
It's not clear, right? It depends on if you measure it by. If you assume that replicas are equally likely to fail, and you measure it by sort of total amount of extra latency added by failures, then it's a wash.
I agree. Right? I understand.
This is better for predictability, though. You'd rather have a larger number of smaller failures than a smaller number of large impact failures?
Possibly, but it turns out from the point of view of an individual request, it's exactly the same.
Let me point out something else.
So the question is it useful to have the system partially functioning some of the time? And it may or may not be, depends on your application.
Let me point out something else, some other way in which EPaxos might be better in this scenario. So if we really do want no client to observe any latency penalty when a replica fails, we can simply propose that command to a quorum of replicas, right? So in this case, the problem is, of course, that we would have lower throughput on the whole, right? Because we propose each command twice in a 3 replicas system. We never have that latency penalty when something fails, but our system has to be able to distinguish between the same command proposed twice, right? And only execute the first one.
Yeah, you got to be really careful with that, right?
No, but that's
an idempotent.
No, because you would have to do that for multi-Paxos as well. Because imagine a client that has sent a command to a leader that fails, and it resends that command, that same command, to another leader. So any.
But in that case, only one of those will ever. If you do it correctly, only one of those is ever accepted. So you don't ever.
I don't think so.
No.
The leader.
Trust me, it is in Smarter. It absolutely has that property in Smarter.
And you don't use any client per client IDs for commands.
No, there is per client ID.
Well, then that's probably why it works in Smarter.
Yeah.
And that's how you would solve it.
I mean, the way that it so.
And that's how you would solve it in EPaxos.
Right. Yes, you could do the same thing.
Yep.
You two will have a whiteboard later to hash this out.
Any other questions? If not, let's thank the speaker again.
Thank you.